So good morning once again, everyone. It's great to see all of you here, and you keep adding your names to the list. And there are three reasons for why we are hosting this workshop today. One is that the United Nations have proclaimed 2025 the International Year of Quantum Science and Technology, or IYQ, to mark 100 years of modern quantum mechanics. The year-long celebration of IYQ aims to raise awareness about quantum science and technology around the globe. And throughout 2025, various events and activities will be organized worldwide to promote quantum science, technology, and education. And this event is one of them. And the second reason for organizing this webinar is because Sweden and the US have a joint statement on cooperation in quantum information science and technology, and that has been in place since 2022. And this agreement aims to enhance bilateral collaboration on quantum, emphasizing the potential importance of quantum science for applications such as climate models, battery technologies, new medicines, and carbon capture materials. And the statement encourages joint research project, joint educational activities to develop a skilled quantum workforce, and sharing of resources and expertise to advance quantum technologies. And the third reason for this event is that there is a network called SIREUS, consisting of 10 Swedish universities and 13 American universities that are committed to increase bilateral research cooperation in scientific fields that are of strategic importance to both countries. And one of those fields is quantum computing, of course, I would say. So for all those reasons, the Embassy of Sweden in Washington is hosting this virtual workshop in collaboration with the SIREUS team. And our goal today is to bring together experts from Sweden and the United States to share their insights on recent developments in quantum computing and to explore opportunities for increased bilateral research cooperation in this field. And we have chosen to focus on quantum computing because quantum science and technology, that's such an extremely broad field. So we want to narrow it down to facilitate collaboration, because if you're a researcher on quantum sensing, you might not have so much to do with quantum computing. That might be the case. So we focus on quantum computing today. And our agenda features keynote remarks from two distinguished leaders in the field, a Q&A session with the keynote speakers, speed presentations by, I think we now have 2 participants. We'd like to open it up for 1 or 2 more if anyone in the audience would like to give a speed presentation later on in the program. And we will end with a joint Q&A with all speakers. So I hope that this workshop will foster meaningful discussions among you that have joined and potentially lead to new collaborations that will contribute to the future of quantum computing. And now it's time to introduce our first keynote speaker, Professor Göran Johansson. Professor Johansson is a full professor at Chalmers University of Technology in Göteborg and the director of the Wallenberg Center for Quantum Technology. He is deeply engaged in quantum physics and technology, particularly in building quantum computers that leverage superposition and entanglement. His work explores how quantum computing can revolutionize medicine and AI by solving problems beyond classical supercomputers. Professor Johansson, the mic is yours.
Oh, thank you very much, Maria. I'll then try to share my screen here. And then so I hope you can see my presentation.
We see it.
Yes.
We see it.
Thank you very much. So yes, I'll briefly discuss what we are doing on quantum computing in Sweden from the perspective of the Wallenberg Center for Quantum Technology. And yeah, before doing that, I just show you my favorite slide describing why it's interesting to figure out what quantum physics can do for computing. And that's because quantum physics really collides with common sense. So here in Sweden, we typically go on at least 1 week of skiing holidays every year. And yeah, my experience is more like the one to the right, but we understand fully that electrons, they do things like the skier to the left. So if they see an obstacle, they can explore both options to go right or left, in some sense simultaneously. And the idea of the second quantum revolution or quantum technology is to build on our thorough understanding of quantum physics and explore these things that are colliding with common sense to get better sensors, more secure communication, and also qualitatively more powerful computation. And in Sweden, a lot of the activities in quantum technology are within the Wallenberg Center for Quantum Technology. So it's a center with around a little bit more than 200 people involved. It's led from Chalmers University in Gothenburg, but it involves universities also KTH in Stockholm and Stockholm University, Lund, Linköping, and Göteborg University. It has two main goals. One is to build broad competence in all of quantum technology in Sweden. And the second one is to build a superconducting quantum computer at Chalmers University. And it's a 12-year program. It started 2018. So we are a little bit more than 7 years ahead, and we have 5 more years to go. And in addition to the universities, we also involve industry partners for larger companies for use cases, and smaller companies and spin-outs for enabling technology. And the funding is depending on the exchange rate, but currently it's $150 million over 12 years. And it's now the International Year of UNESCO's International Year of Quantum. So there, I just would like to show our 10 principal investigators in the center. So to the left, you see people, the 5 people on quantum computing and quantum simulation. And then in the middle, you see quantum communication, the 2 top ones, and the 3 Marcus, Peter, and Anne are our quantum sensing PIs. And there you recognize Anne Luyer. We are very proud to have one of our PIs who is a Nobel Prize laureate 2023. And in this context, she was also giving the keynote speak at the International Year of Quantum inauguration in Paris, 4th of February. So we are very proud of that. And up third column to the right, you see Per Delsing. Some of you might know. So he was building up the center and was the director until the end of last year. So coming to quantum computing, our quantum computer project, or core project as we call it, is led by Giovanna Tancredi, so one of our PIs. And currently, it's a state of tuning up a 25 qubit processor, and which, since it's a superconducting quantum computer, you need to keep it cold. So that's this beautiful chandelier kind of apparatus that you see to the right. It's called a dilution cryostat, and it cools down the chip to 10 millikelvin, so roughly 1/100th of a degree above absolute zero. And the chips are fabricated at Chalmers in our clean room, and the goal of the project is to reach 100 qubits. This is a more in detailed look at how the chip looks. So we have an array of 5 by 5 so-called transmon qubits, and then there are couplers, 40 couplers, so each neighboring, so yeah, at each cross of this 5 by 5 array, there's a qubit, and then each line in between is a coupler. And the qubits they are on one chip, and the control lines on another chip, and then you actually just put them together with the flip chip techniques, and that's why the chip to the left here looks so boring, because it's the backside of the qubit chip actually. Currently, this flip chip technique is done at VTT in Helsinki in Finland, but now we are currently installing a flip chip bonder at Chalmers, and we have good qubits. They have good so-called coherence times, so we can do many operations on them before they lose their quantumness, and this is also improving. Just the figures to the right to illustrate this. We have started a testbed. So it has also with the funding from Knut and Alice Wallenberg's foundation, and it has 3 components. One is the quantum help desk, where if you want to try out a quantum use case for quantum computing, you can ask these trained people to how to do that. You can also get access to the IBM quantum computers, so premium access through this for Swedish researchers. And then we have a quantum hardware testbed where our spinouts can try their quantum computing hardware components. And then we also have the quantum algorithm testbed where we'll give access to our 25 qubit chip later this year, and then also when we scale up to larger processors. Together with our industry partners, we are exploring different use cases. So, for example, with AstraZeneca, a medical company, we look into quantum chemistry, how to model larger molecules on a quantum computer. Together with University Hospital called Sahlgrenska, we're looking into protein folding. And we are also looking into logistics optimization together with a Boeing-owned company called Jeppesen and the Volvo group, which is, where you also have Volvo trucks. And since this is a US-Sweden workshop, I just want to give examples of collaborations that we have already. So Sweden's Minister of Education has signed a bilateral quantum cooperation statement with the US. So Sweden is participating in so-called multilateral dialogues on quantum with the US and 11 additional countries. In the VACT Scientific Advisory Board, it's led by Steve Gervin from Yale University, and we also have Will Oliver from MIT there. We have VACT PI Jonas Belander, who is a co-founder of an MIT spin-out called Atlantic Quantum, which also used the Chalmers cleanroom. And we have a number of scientific collaborations between MIT and Chalmers on qubits and giant atoms and so on. We have a spin-out from VACT called Scaling Q or Scaling, and we know that they are providing some customers in the US with sample holders, so these microwave designed parts of the chandelier where you can put the chip. And as mentioned, VACT is also enabling premium access for the IBM quantum computers to Swedish researchers. We have a collaboration with Cleveland Clinic on protein folding. And we also have ongoing discussions with the Advanced Quantum Testbed at Lawrence Berkeley National Lab, which I guess we will hear more about very soon, about exchanging chips and so on. And I also want to mention that there was a research bill presented from the Swedish government in late December or in December last year, and that contains a number of earmarked efforts on quantum technology, and we are waiting for this pass through Parliament, but we are really looking forward to an increased funding from the Swedish government on quantum technology. So with that, I would like to thank you for your attention.
Thank you so much, Aaron. That was super interesting, and I'm happy to see that you have so many collaborations ongoing already. I also really would like to be that electron in the ski slope. That would make it much easier for me. I have so many questions, but we will save the questions for you until after Kastra's presentation as well. So, and then after Kastra, we will open up for questions first from me and then from all of you listening in. So now I'd like to introduce Dr. Kastra Novrozi. Is that Novrozi?
Yes.
Dr. Novrozi is a research scientist and head of hardware at U.S. Department of Energy's Advanced Quantum Testbed Program, AQT, at Lawrence Berkeley National Lab, where he oversees the development and deployment of full-stack superconducting quantum computing platforms for collaborative research. And his research interests include optimal quantum computing architecture through deep co-design of the layers of the quantum computing stack. Kastra has a PhD in applied physics and a bachelor in electrical engineering and computer sciences, both from UC Berkeley. And now, Kastra, I hand it over to you. The mic is yours.
Thank you so much, Maria. Thank you for having me here, and great to see you, Ron. Thank you for your wonderful talk. So yes, today, if I can share my screen here, I will tell you a little bit about the efforts we have going on at Lawrence Berkeley National Lab, particularly the Advanced Quantum Testbed. So yes, my name is Kastra Novrozi. I am a scientist at the National Lab and also the head of hardware at the Advanced Quantum Testbed. So before I tell you about the quantum efforts, just to set the stage, a little bit of background about Lawrence Berkeley National Laboratory. So the Berkeley Lab is one of 17 U.S. Department of Energy national labs and the birthplace of the National Lab system. We operate a very multidisciplinary set of programs in almost all areas of science. Total of 16 Nobel Prize laureates so far, and an annual budget of 1.5 billion. And among the more than 20 divisions that we have, 5 of them are national user facilities that I have noted down here, some of which are quite relevant to quantum computing. So for example, in particular, I have 3 of the user facilities listed here: the Advanced Light Source, which is our synchrotron facility, similar to Max4, what you have in Lund there in Sweden. We have the Molecular Foundry, which is also another facility with a range of electron microscopes and other characterization tools that engages in theory, simulation, synthesis, and characterization of materials. And then we are also home to the NERSC supercomputing facility that is also a user facility and serves more than 1,000 users. So all of these facilities are open to researchers from around the world through a proposal process to run their experiments. Now, on the second half of the screen here below, I have 3 programs in quantum computing and networking. In particular, of course, the Advanced Quantum Testbed, which is one of the 2 national test beds that we have on in the U.S. Department of Energy, and also the Quantum Systems Accelerator, one of 5 National Quantum Initiative centers headquartered at Berkeley Lab as well, in addition to QuantNet, which is a quantum networking testbed program as well. So with that as the background, I'll tell you a little bit about the Advanced Quantum Testbed. As I mentioned, it's one of the 2 testbeds that DOE runs, the other one being QScout, which is based on trapped ions at Sandia. AQT is the superconducting testbed. So I have some of the principles of our modes of operation and engagement with the community listed here. Of course, we build full stack quantum computers, but we provide low-level access to community. So this means that, of course, we're very transparent with all of our data and characterizations and information about our systems. But once we accept collaborations, we provide any level of access to the hardware, to the control system, to software, algorithms, to modify anything at will in the interest of accomplishing the goals of the collaborative project. We engage in partnerships and free exchange of information. So when we accept user projects from the community, the outputs are all published. They're all up for joint publication. And often what we find is that the output of one user project ends up finding application to enable other user projects, and it turns into a virtuous cycle. And then on the technical side, everything we do, because we have this full stack that we work on, that enables us to have the opportunity to do co-design of the layers of the stack, including at the algorithm layer and throughout the hardware as well. So if you go to our website here at aqt.lbl.gov, you'll be able to find a 3D virtual tour of some of our labs, including our fabrication clean room and also some of our measurement labs, and with some description of what you see here. So I have listed here some examples of what I mean by the full stack. Of course, we engage in development of quantum processing units, of different architectures, different connectivities and different coupling schemes. And we publish all of this. Of course, we do this at lower scale than what you find in industry. The aim is really to explore the horizontal design space of quantum processors. We have the cryogenics. We have the control system. This is a significant part of what we do. Since the control system sits in the middle of the stack, it can be quite enabling. And then the software. Then we have the system integration. So from the perspective of the user who sits here at the top, the user can generate their experiments, their quantum experiments, through a number of openly available platforms, such as Qiskit. On the other end, the execution happens through a range of control systems that we have. And then in the middle, what we have developed is a software stack as well, that integrates a number of optimization tools, such as the Berkeley Quantum Synthesis Toolkit, or BISKIT as we call it, to shorten the depth of these experiments with minimal loss in accuracy of the overall equivalent unit area of the experiment. So once you have all of that, then you can engage in research. And here I have, this slide is from my colleague Ravi Nayak, who's the head of measurement at AQT. This is not a disjoint partitioning of the experimental space, but just a way to wrap our heads around the different aspects. So we have quantum characterization, verification, and validation, QCVV, that involves a set of tools to characterize and mitigate different sources of noise and error. We have novel quantum control, that's multi-qubit gates, ternary quantum logic, compilation, and more. And really, once you have this first two, then you can apply it to do more productive simulations of nature, including quantum chemistry, nuclear physics, and nuclear spin dynamics, and many-body physics, and more. And we have engaged in research in all of these areas. I have some of the publications down here. And we're open to basically taking any of these further. So a little bit more about the quantum architecture aspect of what we do, which is my own personal interest as well, and the team that I've been building here. I have here basically a caricature of the comparison of development of computers classically versus quantum. And if you study the history of development of classical computers, the way we might understand them, not going back thousands of years, but just over the last 100 years or so, you have So what I have down here is the von Neumann architecture as we might recognize it today. But this was really developed hand in hand with the engineering of the optimal classical computer, and the two kind of evolved together as a result of multidisciplinary teams working together under the same roof. And what we've had in quantum has been a little bit upside down compared to this. There has been some version of this abstraction model for quantum computers that has been around for the last 10, 15 years since the very first proof of principle devices. And this has been basically imposed top down, and teams have been put together to address different aspects of this and optimize in their own direction. Which has been kind of a necessary evil. It has been productive because it has enabled groups without access to full stack quantum computers to still engage in research and do their part of the problem. But if, sometimes we adhere to this too closely and then we miss out the opportunities for co-design. And I have here on the very right-hand side, kind of a schematic of the full stack in less detail, starting with the abstraction and algorithms at the very top and the quantum processing unit at the very bottom. And then in the middle, you have QCVB protocols, compilation and optimization, and control system, which sits in the middle. So is there a way to do this more optimally is basically what I'm going to spend maybe 2 slides, 3 slides, just giving you an example, not really digging in detail so much, but just a flavor. And the control system and control compilation QCBB, really the control stack sitting in the middle, is very strategically located to engage in this kind of research, because this is the part that has to worry about both algorithms and the quantum processing unit together. Usually the QPU people would rather not have to worry about application and algorithms, and the application people would rather not have to think about how the QPU is implemented. So in order to enable us to do this kind of research, we've been developing our own open source control system called Cubic since 2018. This started by Gong Huang and Yilun Xu back in 2018. And we developed both the control system based on openly available Xilinx boards, and also developed auxiliary RF components and electronics, which also have been all open source. And then built protocols, including automated calibration protocols on top of this, which were also published. Then over the last couple of years, we've developed Cubic 2.0, which is based on 3rd generation Xilinx boards with more capabilities. We've developed a distributed processor architecture on FPGA in this system that enables us to do mid-circuit measurement and feed forward with arbitrary logic in between, which has, for example, enabled us to do these teleportation-based gates that can bypass the limitations of the topology of the quantum processor. And then we've demonstrated multi-platform synchronization of this as well to make sure that we are able to scale up as needed. And this is the team here: Gong Huang, Yilun Xu, Anile Fruitwala, Abhiraja Gopala, and Anastasia Buko, that I've had the pleasure of leading over the last few years. That was the core group. Of course, there's many more people involved as well. So an example of how this comes into play, randomized compiling. Many of you in the field are probably familiar with this. It's now a commonplace protocol that everyone uses, including in industry. It's a way to mitigate sources of noise and error. In particular, this protocol converts coherent errors into stochastic noise, which is more manageable. And it does so by inserting random Pauli twirling gates between, before and after the hard gates, 2-qubit gates in the circuit, and then computing the undoing Pauli and absorbing it into the existing gates to arrive at a circuit that is logically equivalent to the initial circuit, and also has the same depth, but it just takes a different path to the solution. And so you do this many times, and essentially the effect is to average out coherent error and convert them into stochastic noise, which is more manageable. It is extremely effective, and we've shown that this reduces the total variational distance to the correct solution. Notably, I should mention that this was the project, it was a user project at AQT. It was proposed by Joel Emerson and Joel Wallman, professors at University of Waterloo, who founded the Quantum Benchmark and needed deep access to a quantum computer to demonstrate this. And they worked with us, and because they had disclosed the IP beforehand, and they had their own IP on it, they were able to retain it, and we worked together and we published jointly. So this is one of the success stories of us working together with industry as well. So now this is very effective, but the price you pay is all of these extra compilations. And so if you're, let's say, if you're running 10,000 shots of a circuit and you want to randomize every shot, that is extremely expensive in compilation time and upload and execution. And so what we've done here on Cubic is to develop a way to get around this compilation problem. And without getting into too much detail outside the scope of this talk, I'll just say briefly that this involves several steps that effectively run randomized compiling live on FPGA without compiling beforehand. So it is run on the bare circuit at execution time, and the effect is we effectively get randomized compiling completely for free without any overhead. So I have a few examples here. If we're doing 1,000 shots with 20 randomizations, which is a compromise that is often made, for a circuit width of 8 and a circuit depth of 100, it could take about 12 seconds to execute. If you were to randomize every shot, it would take 500 seconds. And what we're doing here with hyper-efficient randomized compiling is 2 seconds for one randomization per shot, which is just as long as it would take to do it to do the bare experiment. And this was work that was done by Nilay Fruitwala and Akla Hashim. It was led by them. It's on archive since a few months ago. And we have filed a patent on this, but we're making it freely available to research groups to collaborate and to develop further.
Kasra, I'd like to ask you to wrap up soon, if possible.
Yes, absolutely. Yeah. So this is my last. I was going to say that I'm going to bypass. I'm going to not show this other slide, which is another example, but this is my final slide, and just to remind us that this is where we started, and what I have shown is an example of co-designing the middle of the stack and arriving at execution efficiency improvements in that way. And there's more to do to achieve even more gains. And the claim here is that the first demonstrations of useful quantum computing, given the same technology node, this will be enabled by full stack co-design. And so this is arguing for this work in quantum computing architecture. And I'll stop here.
Thank you so much, Kasra. And I'm so happy that you the randomized compiling, to me that was super complicated. So now that you, I mean, what I figure is that you find a way to do that more integrated so that you won't have that sort of extra complicated step in the middle. Yeah, so sounds very good.
Thank you.
I'd like to, we're a bit behind schedule, so I just like to ask both of you, Göran and Kasra, so what do you, from these presentations, and I know that you know a lot about each other's, the test beds already, but what would you say for me and the audience who don't know the details, what are your test beds, what are the sort of most significant differences between them?
I could say that, so we are trying to scale up to more qubits. So our aim is to go to a demonstrator of 100 qubits, which I mean, we are at the same time trying to give our users the same kind of access to low-level control and so on. But I think that this aim to scale up the system, I think that might be a difference. Or yeah, Kasra, what do you say?
Yeah, we definitely have been deprioritizing scale, and that is one difference. I think another area I would point out is For us, the testbed is not really separate from the research program. It's one and the same. Really, the testbed is just an avenue to enable us to do collaborative research with our users jointly together, not something where, and in fact, anything that can be done elsewhere doesn't require full deep access to the testbed, to the quantum computer. We don't really accept the proposals. Yeah, that's another difference in modes of operation.